So now we're going to talk about some principles relevant to covariance and correlation matrices. This video is essentially just a review about things we talked about, but I'm going to try to connect them together. And we're going to talk about the relationship between matrix operations and the various matrices in the process of creating both a covariance and a correlation matrix. So our first one that I'm going to discuss is the SSCP, the sums of squares and cross products matrix, which we have found to be the transpose of the raw data times the transpose. And in the previous video we used our raw data, we had the matrix with the values of 8, 5, 6, 7, 4, 11, 6, 5, 10, and 3, 2, 9. Now this is pretty simple. It's just basic matrix multiplication applied to this X matrix, which is the raw data. And then we have variables as the columns, and as the rows we have observation units, which we have in this case n equals 4 because we have 4 rows. Now this is a special case of matrix multiplication. It's matrix multiplication applied to a particular kind of matrix, which we'll say is a observations by variables data matrix. So it's a R by C, rows by columns, which is our observations on the rows by variables. So once again, it's a special case of matrix multiplication applied to an observations by variables data matrix. The next one I want to talk about is the centered sums of squares and cross products matrix, which we know to be the deviation score transpose matrix times the deviation score matrix, which we also have found to be the transpose of the raw scores times the deviation scores. Now this is a special case or restricted case of the sums of squares and cross products matrix, which in the last video we also showed that you take the sums of squares and cross products matrix and you subtract by the total times the transpose of the mean vector matrices there, and that will just center the sums of squares and cross products matrix. But the one we'll use most is this one right here because it's most simple and it's most precise. So once again, matrix multiplication of data matrices that are centered is this one. So we can use the first one to get the second one. The third one is the covariance matrix. This is even more restricted than the centered sum of squares and cross products matrix. It's the CSSCP divided by the DF, which is the degrees of freedom. So we denote the covariance matrix with C, and it's basically 1 over n minus 1, or remember n is our observations, and we know that degrees of freedom is n minus 1, times, we're going to call the CSSCP, just to make it short, we're going to call it B, okay? So it's going to be B. So basically, once again, you take the centered sums of squares and cross products and divide by the degrees of freedom, or multiply, since we're doing matrix multiplication, matrices here, you can't divide by a matrix, you have to multiply by the inverse. Don't forget that variances are on the diagonals and covariances are on the off diagonals. So we need the second one to get the third one, and guess what the fourth one is? I'll give you 100 points to whoever can guess it. Alright, you all get 100 points. It is the correlation matrix. And how do you get that? You get this by standardizing the covariance matrix. So it's the covariance matrix adjusted for its standard deviations. This is the most restricted and most specific special case. Remember that the covariance that we found algebraically to be the sum of xy over n minus 1 degrees of freedom, and that the correlation matrix, which we usually denote correlations with R, the correlation is just the covariance standardized. So you divide by the standard deviations of both x and y. We also said to get a matrix, the correlation matrix, which we denote with R, is E times the covariance matrix times E, where E is in fact the inverse matrix. What's the inverse of? It's the inverse of the square root matrix of the diagonal matrix of C. Wow, that's a lot of parentheses. But we showed that in a previous video. This is just a summary of the principles that are relevant to covariance and correlation matrices. So we see that these go in succession. You can use 1 to get 2, you need 2 to get 3, and you need 3, the covariance matrix, to get 4, the correlation matrix. Do you have any questions? Raise your hand if you do. All right. Very good. I hope you have a good day.